All right, so from previous work we know a little bit about the chain rule, right? The way I have done it, or the way I kind of wrote it out last time we visited the chain rule was, say we've got y with an inside and outside function, and that's going to be a little different here, but let's kind of make the analogy here. So the chain rule, by the chain rule, we've got the derivative of this would be, the derivative of the outside, the inside the same, and then times it by the derivative of the inside, all right? That was our chain rule. Well, let's alter this just a little bit up and change a little bit of the notation. Let's call this g of x a new function, right? Okay. Let's say that's u. U is g of x, so we've got y equals f as a function of u, which means that our f prime, derivative of that, but then u, we have to do the derivative of it, which is, of course, g prime x. I mean, it didn't really change much, but here's what I was wanting to get to. This derivative, which, going off the original here, let's change this to Leibniz, is really what I'm getting to here, because I haven't really emphasized the chain rule in the Leibniz notation. All right, so this would be, y prime would just be dy dx. Then this f prime would be what? Well, that's the derivative, if we're going off of these two things here. F prime of u, well, that would be the derivative of y with respect to u, right? And then g prime, that would be the derivative of the u with respect to x. Okay. So it's just a little different way of thinking about the chain rule, but in Leibniz notation, this is what the chain rule looks like. And that's more what we're going to play off today. The chain rule, because now what we're going to do is we're talking about functions of two or more variables, right? Z is f of x, y. But anyway, that's what the chain rule looks like in this Leibniz notation. Okay. So let's suppose we've got z, like I said, z is a function of x and y, okay? And where the inside and outside part comes in, x is also going to be a function of something, and we'll use different things, but you can kind of think of it to kind of get an idea. All right, so z is changing as x and y are changing, but what if x and y are changing as, say, as a function of time? So x is some function of time. Let's call it g of time. And then y also is changing as a function of time. Okay. H there. Okay. So the idea here is, we talked about, in this case, we'd have partial derivatives of f with respect to x. But what if we were wanting, in this case, couldn't we think of dz dt? dz dt. Because essentially what we're saying here is, yeah, z is a function of x and y, and x are a function of time. So essentially, isn't z a function of time? And so we can think of the derivative of z with respect to time. In other words, what happens if we change the time just a little bit? Well, that's going to, of course, change the value of z too. And that's going to change as you go along, because these are all functions of things. So that's what we want to come up with as a way to determine dz dt, the derivative of z with respect to t, given this stuff here. And that, again, is kind of a, it is kind of a an inside-outside thing, because if you think about it, we've got z as a function of x and y, but then x and y are themselves functions, and so you've got inside functions here, right? And so that's how this is analogous to what we've talked about before, the inside-outside thing. But we are not going to directly, anyway, just substitute these in and then do our inside and outside thing. We're going to just kind of think of it in the Leibniz terminology. Well, it turns out that this dz dt, and you can, the book goes into how you prove this using the definition basically of derivatives or partial derivatives. Turns out dz dt is, well, you do the partial derivative of z, this function, with respect to x, and multiply that by then the derivative of x with respect to t. And then add to that, you do the very same thing basically with the y's. You do the partial of z with respect to y times dy dt. Okay? So it's kind of like, what did we say dy dx was? The chain rule, it was dy du times du dx, right? And so this, because now we have, instead of, if you will, the dependent variable y with independent variable x, we've got, well, we'll talk about what we call these variables here. Yeah, we've got x and y. Z is a function of x and y instead of y just being a function of one variable. Z is a function of two variables. And so you need two of these basically for z, the ones with the x's and the ones with the y's. Like I said, it goes into the details of the proof there in the book, but that's essentially what you're doing. You're just doing that y and the x's separately, and then add those two together. All right, so let's do one here. So let's find dz dt if z equals x squared y, x equals cosine of t, and y equals sine of t. Okay, so dz dt equals the partial of z with respect to x, and then we do dx dt, and then do the partial of z with respect to y times dy dt. Okay, so what do we got here? What's our partial of z with respect to x? Well, the partial just means we're holding the y constant, so the partial would be 2xy, right? dx dt, well then we're just doing the derivative of x with respect to t, so that would be negative sine of t. Then we just reverse that and do it with the y's, so dy, the partial of z with respect to y would be just x squared. And then dy dt would just be cosine t. Okay? And so that would just be, clean it up just a bit, negative 2xy sine of t plus x squared cosine t. Okay? Now, I think sometimes that's the way maybe they give the answer there in the book. But let me point out here too that if we wanted, we're doing dz dt, if we wanted this just in terms of t, we could do it. You know, this still has x and y in it. But don't we know what x is in terms of t and what y is in terms of t? So if they want it just in terms of t, which I'm not sure, yeah, just substitute x here. X is cosine t. The y is sine t. And then same thing here. This would be x squared, so it would be cosine squared t times cosine t. And so that does look, cleans up a little bit, doesn't it? 2 cosine t sine squared t we would have here, and then cosine cubed t we would have here. So anyway, if they want it just in terms of t, we can do that as well. All right. Now, one other thing that we could do here is then, of course, talk about, let's see if I can. All right, so let's find dz dt if t equals pi over 3. And so now, yeah, now we can do the actual value, find the derivative of z with respect to t, because, yeah, now we've got, now if we use this version, the only thing is if we use this version, we'd have to find the x value by going back to that. Since we've got this, might as well just use that. It would be -2 times the cosine of pi over 3 times the sine of pi over 3 cubed, cubed squared, sorry, plus then the cosine of pi over 3 cubed. Yeah, so it's just a matter of plugging in then, isn't it? So the cosine of pi over 3, 1/2. And sine of pi over 3 is square root of 3 over 2. We're going to square that. And then the cosine pi over 3 again, so it'll be 1/2 cubed. So that would be -1 times 3/4 plus 1/8. So that is be -6/8, so that'd be -5/8. Is that what you got? Okay. Okay. All right. So let me do one more of those, and then we'll move on to another here. Okay, all right. So let's see. Let's find dz dt if z equals x squared minus sine of xy, x equals e to the 2t, y equals t squared minus t plus 4. Okay. So dz dt. To do it, we do what? We do the partial of z with respect to x times dx dt. And then do it with the y, so partial of z with respect to y, dy dt. And notice here, you know, I'm using the partial here, but then the dx dt on this part. Why is that? Why do you use partial here and then dx dt here? Well, that's because, yeah, z is in terms of x and y, but x is only in terms of t, so it's one variable. So that's kind of why the notation looks like that instead of, you know, both be partials. But anyway. All right, so what do we got? Partial of z with respect to x. So that'd be 2x, and then that, what about that? Minus cosine xy, yeah, times 1, all right. Yeah, there is a chain rule in that, isn't it? But it just, well, y. The derivative of the inside part, we'd have to consider that. Okay. Times, so that's the partial of z with respect to x. Then dx dt, it'd be a little easier, won't it? Just the derivative of that with respect to t, so that would be 2e to the 2t. All right. That's the first part. The partial of z with respect to y. Okay, so we're back to z here, but we're doing the partial of z with respect to y, so that'd be 0. The x is constant. So it'd be negative cosine of xy again. But then the derivative of the xy with respect to y would be x, yeah. And then multiply that by dy dt, which here's y, so dy dt would be 2t minus 1. Like I said, I think they leave it in terms of the x and y, so not a whole lot to do to clean. We'd probably write the 2e to the 2t right out here, in the parentheses 2x minus, and let's write the y first so we don't get that confused. Do it like that. And then this, of course, would be minus, let's just say x cosine of xy times 2t minus 1. Something like that. Now, one point to be made here. What was that first one I did? Z was x squared y. X was cosine t. Y was sine of t. Okay. This one, that one, we could have done it. We could have done it without doing this, because couldn't we, first of all, just substituted those in and got z equals cosine squared t times sine of t, and then dz dt is just a product rule with the chain rule. However, what it turns out, the reason this way is preferred is because when we get something like that, it's much more complicated to substitute the x and the y in there and do some rules on it than it is this right here. I mean, this was complicated enough, but think about it, if I plug those in here, the x and the y here, then you've got multiple things going on to keep track of and everything. So it's usually less complicated to do it this way than it is to substitute and do it that way. You could do it that way, but it, for one thing, if you don't substitute back in for the x and the y, it's going to be much more compacted. Well, no, I'm just pointing out that you could have done it that way, but when you get more complicated stuff, it is much easier to do it this way. Okay, just kind of making the connection there. All right. Now, the other thing, let me point out here, I kind of mentioned it a second ago, but you know what is kind of the reasoning behind this? When would this occur? Well, like I said, if we think of this right here as maybe the path of a particle, the x equals 2t, y equals t squared minus t plus 4. You know, we did stuff like that back when we were talking about parametric equations. Let's say that represents the path of a particle. You know, at time t. And I think it looks like something like this. So as you start at time t equals 0, you're up there. I'm not sure, but anyway, if we took time and graphed it, you got, this is kind of the path of the particle. It's just kind of swooping down. Okay, now, then where this would come in, maybe think of it like a temperature. Say this is the temperature at a certain xy value. And so, your path is changing, but then this also gives us the change in the temperature as you go along that path. And so you see two things at work, the path of the particle, and then you also have the temperature changing as it goes along that path, you see. So that's kind of the idea here. So many things at work. Okay. All right.